All right, let's talk about a piece of tech where being pretty close just doesn't cut it at all. We're diving into the Vaisala WXT536. It's a weather sensor where insane accuracy isn't just a nice feature. It's literally a matter of safety and keeping things running smoothly.
So, to really get why this is so important, let me ask you a question. Think about something like aviation or a huge industrial plant. What do you think happens if a sensor is off by just a single degree Celsius? Just one. What's the big deal, right?
Well, the answer is it's a very big deal. It can be a catastrophe.
And no, that's not being dramatic. A tiny little error in the data can have this massive ripple effect, leading to some truly disastrous consequences in the real world.
Just look at what can happen. For a pilot, being off by 1 degree in the dew point calculation could mean you completely miss the warning signs for aircraft icing. In a gas plant, a little drift in a humidity reading could, create the perfect conditions for chemical instability. And it even affects the hardware itself. Get the humidity wrong and you might not realize that your super expensive equipment is corroding way faster than it should be. The stakes are just incredibly high.
So, the big question is, how do you even begin to build a device that prevents these kinds of failures? Well, the first part of the answer is actually in the physical design. And this, right here, is the game changer. Think about old-school weather stations. They've got those little spinning cups for wind speed, right? Those are mechanical parts. They wear out, they get stuck, and in cold weather, they can literally just freeze solid. Total failure. But the WXT536? It's solid state, no moving parts. It uses things like ultrasonic transducers to measure wind. That means it is unbelievably reliable and barely needs any maintenance, which is exactly what you want on an offshore oil rig or at a busy airport.
Okay, so we've got this super tough physical sensor, but how does it take what it's sensing out in the real world and turn it into a digital signal that you can actually trust?
It all starts with speaking the right language. The sensor uses something called Modbus RTU, which is basically the universal language for industrial gear. This means the data it collects can be perfectly understood by the main control systems, and it's all sent over a super tough physical connection called RS-485, which is designed to work flawlessly over long distances, even in really noisy industrial environments.
Now, get this, the level of detail it captures is just immense. Inside this thing is a 24-bit analog to digital converter. The best way to think about it is like having a camera with an insane number of megapixels, but for air pressure. It captures the absolute tiniest changes, making sure nothing important gets lost when you go from the real world to the digital one.
So what happens to all that data? Well, it's a 3-step journey. First, you get the raw data, but that data can be kind of messy, full of what you might call statistical noise. So next, a really smart filter gets applied to clean it all up. And what you're left with is a pure, clean signal you can rely on.
This special filter is called an exponential moving average. Here's a great way to picture it. Imagine you're trying to measure the true depth of the ocean, but there are waves on the surface. Those waves are the noise. This filter is a mathematical way of smoothing out all those waves, that statistical turbulence, so you can see the real, steady water level underneath. It just massively boosts the actual signal over all the background noise.
So now we have a clean signal. It's high resolution, it's stable, but that leads us to maybe the most important question of all. How in the world do we know that it's correct?
The answer comes down to one absolutely critical process: calibration. And this quote from the source material says it all perfectly. Calibration ensures that our digital measurements reflect the physical reality. It's the step that ties everything the sensor says back to the real world.
And we're not just talking about a quick check. There has to be one single authoritative source of truth. For a sensor like this, all calibration is benchmarked against a NIST traceable standard. That's the National Institute of Standards and Technology. It's the ultimate ground truth that every single sensor has to be perfectly aligned with, no exceptions.
The whole procedure is just incredibly precise. First, they take the sensor and hook it up to a master computer. Then it goes into a special climate chamber to stabilize. The technicians then take a reading, the as-found data, and compare it against that NIST reference. If it's off, even by a tiny bit, they apply a very specific mathematical correction in the software. And finally, they check it again to verify the as-left data, making sure it's now dead on.
And this isn't guesswork, it's pure math. The source even gives us an example of what this fix looks like. A tiny offset was found, so this exact formula, y equals 1.0 times x minus 2.5, was programmed right into the sensor's software. It's a surgical adjustment to bring its readings back into perfect alignment.
And all of that, the tough, solid-state design, the advanced signal processing, this obsessive calibration, it all leads to the final result.
And the final verdict is just one simple word, but it means everything: pass. That confirms the sensor is accurate against the ultimate standard, and it's ready to be sent out into the field where its accuracy is absolutely non-negotiable.
Which brings us right back to where we started. This whole incredible, detailed process of engineering and verification really exists to answer one fundamental question. When lives and safety are on the line, is close enough ever really good enough?